Hello Chem 1B, this is chapter 16, lecture video 9, and we're going to be talking about polyprotic acids, or acids that have more than one H that can be donated. So one of the things that you have to understand is that when we have a polyprotic acid, we have more than one proton that can be donated to water. So there are multiple equilibriums here. Each donation of one proton is its own equilibrium and has its own unique Ka value. So for instance, if we look at phosphoric acid, which is a triprotic acid, it can donate a single hydrogen to water, form H3O plus and H2PO4 minus, and that has a Ka value of 7.5 times 10 to the negative 3. But then H2PO4 minus can go on and donate another hydrogen to H plus, which forms our two products, H3O plus and HPO4 2 minus. This has a substantially smaller Ka value if you look at it, right? Ka2, which is what we call the second dissociation, is almost like 10,000 times, almost 100,000 times weaker than Ka1. But yet again, HPO4 2 minus can go on one more time to donate its proton to water, forming these products, and it has a Ka of 4.2 times 10 to the negative 13, which is again significantly weaker. Each sequential hydrogen being donated, the Ka value decreases substantially for. Now, if I were to give you, hey, we have a 0.50 molar solution of H3PO4, what's the pH? We would treat this like a weak acid mixture, and really we only care about this first Ka to calculate pH. However, if we wanted to know how much PO4 3 minus was present, we would have to do an ice table here, use the results from this ice table for an ice table here, then use those results for an ice table here, and finally get our answer like we did with our weak acid mixture where we had two weak acids mixed together. So this is, a very tedious problem, but doable based on what we've covered. So let's talk about a very unique acid, and that is H2SO4. H2SO4 is one of our strong acids, but you have to understand that it's actually only its first dissociation that is strong. H2SO4 is a diprotic acid, and the first ionization step is a strong acid dissociation. Again, make sure you note this is a one-way arrow. The second dissociation, where HSO4 minus goes on to dissociate again to form H3O plus and sulfate, is a weak acid dissociation. However, if you look at this value here, it's 10 to the negative 2. It's a pretty dang strong weak acid as far as weak acids go. The second ionization is definitely influenced by the first because we already have an initial concentration of H3O plus in the solution by the time we start ionizing the second step. But we have to take into account both steps because this Ka is substantially large and we can't ignore it. Okay, so let's do a problem involving H2SO4. We have a 0.2 molar solution of H2SO4, and we know the Ka for HSO4 minus is 1.2 times 10 to the negative 2. The first step here to understand is that H2SO4 dissociates one-way arrow into H3O plus, it's technically reacting with water, and HSO4 minus. Now, we have to understand this one-way arrow, so whatever concentration of this guy I have, that's how much I make of H3O plus and HSO4 minus. So I get 0.20 molar H3O plus here and 0.20 molar HSO4 minus. This now can be used in our next part, which is the equilibrium of HSO4 minus. I can fill in an ice table a little bit out of order there, sorry. So I have 0.20 molar of this. I know I don't care about water. I have 0.20 molar H3O plus. Again, from here and here is where I got those two values. I have 0 SO42 minus because I haven't made any yet. And now we can do our change row. Minus x plus x plus x. We get x here. We get 0.20 plus x. We get 0.20 minus x. And these, as you can kind of see, can be put into our Ka. But the problem is, because this is substantially large, you're not going to get away with using the 5% rule here. You're going to need to use the quadratic equation to solve this problem. So let's rearrange it algebraically, right? We're going to multiply both sides by 0.20 minus x. And that will get me something like this, right? Which I can then distribute into my parentheses. Gets me here. And now I can just combine like terms on one side of the equal sign. And if I rearrange, I get this equation. At this point, we can use the quadratic to solve this problem, right? We have negative 0.212, right? Negative b plus or minus the square root of b squared minus 4a times c, right? So 4ac, here's a, here's c, all over 2a, a is 1, right? So I just didn't include it here. If we solve this quadratic, we get this, and then we get the only positive value is 0.011, technically molar, and there's my x. Now, I can plug this x back into my equilibrium row of my ice table, and this gives me 0.2 plus x as my H3O plus concentration, gives me 0.21. I can take the negative log of this to get pH, which gives me a pH of 0.68. This is an incredibly acidic solution. We could then also plug in to get the HSO4 minus concentration in solution, or the SO42 minus concentration, or even the OH minus concentration. At the end of the day, this is how we would solve a problem like this. So if you have any questions, as always, discussion session or email. Again, this is a fairly concentrated solution of sulfuric acids, like 0.2 molar. It's pretty high. Generally, if we had a lower concentration, the X value is going to change these significantly more than it did in this example. But yeah. All right, so again, any questions? As always, you know how to reach me.